necessarily if you don't want. But I'm going to start by going back over and listing all of the limit strategies that we have so far. And actually, we're probably about done with coming up with limit strategies. Again, you don't have to copy this down if you don't want to, but just don't forget, first thing to do in any limit problem is direct substitution. You never know, it might work, so you should try that first. Then, if that doesn't work, factoring, radicals, complex fractions, those are all kind of grouped together actually as the next thing to look for. Hopefully by now you can recognize factoring, when you could factor. Radicals, obviously you have to have a radical. And then complex fractions, we know from there, from yesterday, it has to have a fraction in a fraction. And then you go that approach. If none of that can be done, then I would probably at that point go to the graph and try to figure out the limit just from looking at the graph. It is kind of one of our last resorts because, like we've seen, a lot of our answers are not going to be easy to find on a graph. Like the last one in the homework was -1/16. You can't really see that very well on a graph. So I don't usually do that until I've exhausted all of those other options. And I put table up here just because I didn't want to leave it out. But to be honest, I don't ever use a table unless they tell me to use a table. So that is definitely the last thing you would do. And again, usually that's just what you do if they tell you to use a table. So that's kind of out of the picture for the most part. Okay, now for today's lesson, we are still finding limits, but we're going to be working with some trig functions a little bit more. And so I want to put up here, and this is where you can start writing if you'd like. I want to put 3 of our trig identities from last year that are going to be really helpful today. These are on the back of Handy Dandy, but I'm just going to point out 3 of them that I know for sure you are going to use. Okay, this first one was called a quotient identity. Tangent of x equals sine of x over cosine of x. That was a quotient identity back in trig. We're going to use it again today. Now, you can also take that quotient identity and use it with everything being squared. So you've got tangent squared equals sine squared over cosine squared. And I'm just going to do the old switcheroo and give you cotangent of x, just another quotient identity. And that is going to equal cosine of x over sine of x. It's stuff that we've talked about before. It's on the back of Handy Dandy, but I like to put those 3 up here because that's basically the main ones that we're going to be using. Now, I'm going to get to some new stuff down here. We, in calculus, have 2 what I call special limits involving trig functions. And so, these are definitely ones that you want to write down. I'm going to be using them all day today. If you take the limit as x approaches 0 of sine of x over x, it's going to equal 0. It's kind of a nice limit. A lot of times with trig functions, you don't really end up with nice answers, but that's a nice one. So we use it a lot throughout these problems. The other one that we use a lot, which is also nice, is this one. It's the limit as x approaches 0 of 1 minus cosine of x all over x, and that also turns into 0. Again, they're just nice to use because they equal 0. So if we can use those in our problems, then 0 is pretty darn easy to work with. Okey-doke. So I'm going to leave those up there. You don't have to recopy. That's just going to be really important. So it's still up at the top. And now we'll start to find some limits. It says find the limit if it exists. Pretty sure they're all going to exist today, but find the limit if it exists. For the most part, the only time in here right now that we know of it not existing is if we're looking at the graph. If we do it from a graph, we kind of know a few different times where it would not exist. Okay, so here is example 1. It says the limit as x approaches 0 of 4 sine of x over x. Now, first thing you want to remember is that you can't cross out those x's. It's tempting, but that x is with the sign, so you can't do that. Now, anytime I have a trig function, I guess first I should try to do direct substitution, but I think you're going to get a 0 on bottom. Also, sine of 0 is 0, so the top would be 0. Direct substitution's not going to work. Now, if a trig function is involved, I always want to look for one of those special limits. I want to see if I can find that or that inside my function. Now this one's pretty easy to figure out. I can see sine of x over x in my function. So for my first step up here, I'm going to kind of rewrite this. A lot of times today, it's like you're picking apart the function to make it look like one of those special limits. So I'm just kind of picking this apart. I'm writing it as 4 times sine of x over x. Now, you really don't have to show this next step, but I want to show it to you because it's important that you know what's going on. When we talked about limit properties, the limit of a product, this is 4 times sine of x over x, the limit of a product equals the product of their limits. If you want to write this down, you can, but once you get going with these, this is just kind of something that you do in your head. The limit of 4 times sine of x over x is the same as taking the limit of 4 times the limit of sine of x over x. Now, we also had a property that said the limit of a constant is that constant. So this is where I'm actually going to come up with my answer. The limit of 4 is just going to be 4. Then I come over here, the limit as x approaches 0 of sine of x over x is 0. So to get my answer, I'm just taking 4 times 0, limit of that part times limit of that part. So 4 times 0, that's just going to be 0. Okay, you're looking for those special limits, or sometimes you might be looking for identities that you can spot. And once you find them, try to kind of pick it apart so that you can use those nice limits. Okay, I'm going to keep going here. This is example 2. it is the limit as x approaches 0 of 1 minus cosine of x all over 2x. Plugging in 0 is not going to work. You're going to get a 0 on bottom, and what's cosine of x? Or cosine of 0 is 1. You'd also get a 0 on top. So direct substitution doesn't work. Now I see the trig function, and I'm going to try to match it up to one of my special trig limits. And I obviously am matching up a little bit better to that one, but the only problem is the 2 on bottom. It's not supposed to be 1 minus cosine of x over 2x. It's just supposed to be 1 minus cosine of x over x. So I'm going to kind of do what I did on the last problem, which was, pull that number out front and then have the limit part by itself. But the number that I have to pull out here is not 2. The 2 is actually on bottom. If you want to think about this for a second, this seems kind of weird, but you'll see what I'm doing here in 1 second. If you put that quantity kind of in parentheses by itself and multiply it by 1, you can pull a 1/2 apart. I'm going to do that right here. Pull that 1/2 out front, and so this 1 minus cosine of x over 2x, that is actually going to be the same as 1/2 times 1 minus cosine of x over x. Okay, so I can do what I did on the last problem. Again, if you don't write this step out every time, it's fine. But I can take the limit as x approaches 0 of 1/2 times the limit as x approaches 0 of 1 minus cosine of x over x. The limit of a constant is the constant, and the limit of that is 0. So 1/2 times 0, it's just 0. I realize the first 2 have turned into 0. I can't say that they will always do that, but the first 2 have kind of worked out the same way. You're trying to rewrite the function so that you can find one of those special trig limits in it. Okay, any questions about that one? Stop me if you do have a question. I'm going to keep on rolling here. Example 3, the limit as x approaches pi over 4 of sine squared of x. Well, direct substitution did not work with the first 2, but this doesn't have a fraction in it or anything, so I may actually try to do the direct substitution right off the bat. If I put a pi over 4 right there for x, it's going to say sine squared of pi over 4. Now, instead of thinking of this as sine squared of pi over 4 is the same as the entire sine of pi over 4 squared. It's just a different way to write it. But for this problem, I like to write it like this better than having the square in the middle. You're taking the entire sine of pi over 4 squared. Now, you might be able to do this just on a calculator. I don't know. I like to use handy dandy. Sine of pi over 4 is radical 2 over 2. So, if I have to square that, anytime you square a fraction, you square the top and bottom separately. So the square root of 2 squared is just 2. And then on bottom, 2 squared is 4. So I just need to reduce that, and that would give us a 1/2. Okie doke. Direct substitution. Sometimes we forget about it, but it should always be the first thing that you try. It worked right here on number 3. Alrighty, I'm going to keep going here. I kind of forget how many I have today. This is number 4. The limit as, I've missed theta. I don't know about you guys, but I have missed theta. Haven't used it since trig. The limit as theta approaches 0 of 3 cosine of theta tangent of theta all over theta. Theta is just x. It's a variable. It's a cool looking variable. It's just different. It still works the same way. Okay, now direct substitution, not looking good. Right off the bat, I can see I'm going to get a 0 on bottom. Probably going to end up with a 0 on top, maybe as well. Yeah, so I can't just plug in the 0. Now, I start to look for my special trig limits. I don't see, now you're going to have to think of these as thetas for a second. I don't see sine of theta over theta, and I also don't see 1 minus cosine of theta over theta. I have cosine, but you're not subtracting it from 1. It's not matching up to either of those. So that tells me maybe I have to use some other trig identity to get this simplified. Now, we spend a lot of time with trig identities in trig, but anytime I see cosine and tangent together, or like sine and tangent together, something like that, I immediately think of my quotient identities. What does tangent equal? Sine over cosine. Let's leave 3 cosine of theta alone, but replace tangent of theta with sine of theta over cosine of theta. And this is where good things start to happen. Okay, I'm going to think of this cosine of theta out front here. You can kind of think of that over 1 if you want to, but basically those cosines are now gone, and it has just turned into the limit as theta approaches 0 of 3 sine of theta over theta. Now, you still can't do direct substitution, but now it's matching up to this special limit. X is theta here, and so if you want to kind of think of it like we did on those first couple, 3 sine of theta over theta is the same as 3 times the quantity sine of theta over theta. And again, the limit of a product equals the product of the limits. So the limit as theta approaches 0 of 3 is 3. And the limit as theta approaches 0 of sine of theta over theta is 0. And then 0 times anything is 0. If you have one of those special limits in your function and it's getting multiplied by something, it will always turn into 0, because 0 times anything is 0. I can't say that the answer to all of these is 0, but if it's getting multiplied by 0, then yeah, that should end up being your answer. Alrighty, any questions on number 4? Alright, I think there's 2 more here. So this is number 5. Number 5, the limit as x approaches 0 tangent squared of x all over 4x. All right. Now, I'll be honest, of all the problems today, this one maybe takes the most work. First of all, you can't do direct substitution. It's not going to give you back anything good. So then I try to compare it to one of those. It's not matching up to either one of those limits. So then I start to brainstorm some identities. Now, usually when I use a quotient identity, it's because I see something nice that's going to cross out like we did in the last problem. I don't really see anything that's going to cross out if I do this, but one of the only things I know to do with tangent squared of x is turn it into sine squared over cosine squared using a quotient identity. Now, it's possible that this could work using a different identity. I haven't tried it, but it could work. But let's kind of just stick with the quotient identities today to keep everybody on the same page. Now, this looks pretty messy, but remember when we divide with fractions, we keep, change, flip. So here it is. I'm going to, actually, let me just write out the very next step. I'll keep that out front there, the limit as x approaches 0. And if I keep, change, flip, it's going to say sine squared over cosine squared. I can probably go ahead and stick that up there. Times, because it's not division anymore, it's multiplication, times, instead of 4x, now it's 1 over 4x. Keep, change, flip. All right, it's still not really clicking here too much. I guess one of the next things we could do is just multiply those fractions together. So sine squared of x times 1 is just sine squared of x. Then cosine squared of x times 4x is just 4x cosine squared of x. A lot of times with trig functions, and you maybe remember this from last year in trig, you may not really know where you're going yet until you get to the end. If it doesn't work out, you can go back and try something different. But let me kind of show you a way that we can pull this apart so that we've got some better stuff to work with. I see this 4 on bottom. And again, if you think of a 1 being on top, you could just kind of pull that out front as a 1/4. Now I'm just going to start crossing stuff out as I use it. Okay, I'm keeping in mind my nice trig limits. I don't think we're going to be using that one on this problem because you don't have subtraction anywhere, but you do have a sine of x over x. Technically, you have sine squared, but for the time being, let me just pull one of those sine of x's out, and I'll put sine of x over x. Now really, once you see that this is getting multiplied by something, you probably can tell what your answer is going to be. But if I keep going with this, here's a couple more things that I would do. You still have a sine of x on top, and you've got a cosine squared on bottom. I'm going to pull out just one of those cosines to make it sine of x over cosine of x, because I know that's going to turn into tangent. And then technically, I've gotten rid of all of my sines now. Technically, The only thing that I have left in this is a cosine of x on bottom. So I guess my last little part here would just be 1 over cosine of x. Now, if you actually go through and find the limit of each part separately, remember the limit of a product is the product of the limits. The limit of 1/4 is just going to be 1/4. The limit as x approaches 0 of sine of x over x is 0. I'm going to go ahead and put that there. Then sine of x over cosine of x, if you think of that as tangent of x, I could probably use handy dandy real quick to figure this out. Tangent of 0 is another 0, and then 1 over cosine of x, you could actually use a reciprocal identity on that. That is secant of x. So plug in a 0, and I'm using handy dandy. Secant of 0 is 1. Again, that might have been a little extra work down there at the end, because once you see that you're taking the 0 times something else, the whole thing just ends up being 0. However, it is still important to know how to break that apart, just in case you don't end up with this in your function. If you just have those other single terms, you gotta know how to kind of break those apart. Okay, didn't really know where we were going with that at first, but once you pull everything out, it actually worked out okay. Any questions on number 5? That's a pretty good one. Again, probably the most work of all of them today. Let's try the last one here. Number 6. The limit as x approaches pi over 2 of x cosecant of x. X cosecant of x. Well, first thing to do in any limit problem, plug in the value of x that you are approaching. And I don't really see any problem with this as long as everything works out okay. Pi over 2 times cosecant of pi over 2. I'm just going to use handy dandy real quick on that last part. Cosecant of pi over 2 is 1. So you're actually just taking pi over 2 times 1, which is just pi over 2. Didn't need any identities, didn't need any special trig limits. Direct substitution works. So that's it for number 6. All right. I'm going to put the assignment up here. This should be C20 by now from page 85. We're doing 69 to 77. And please